Okay, next we will discuss the electric potential due to collection of endpoint charges. Consider we have a system of endpoint charges. That we have a charge Q1, then we have another charge Q2, and then we have another charge Q3, and so on up to Qn. Their distances from some reference point is, here it is R1, and here it is R2, here it is R3, and here it is Rn. From this point O, I call this point is point O. Now the potential at point O, the potential at point O, due to charge Q1. Q1 is, I call it V1, which is equal to 1 over 4 pi epsilon naught Q1 over R1. Similarly, and the potential at point O due to charge Q2 is, I call it V2, which is equal to 1 over 4 pi epsilon naught Q2 over R2. And similarly, we have V3 for charge Q3, and finally for charge Qn, the potential at point O will be I call it Vn, which is equal to 1 over 4 pi epsilon naught Qn over Rn. Now the total potential at point O, because potential is a scalar quantity, so we can calculate the total point at point O by taking the sum of all this potential. Total potential at point O will be, its value will be, I call it V, which is equal to V1 plus V2 plus up to Vn. Now if I put the value, in each term we have this 1 over 4 pi epsilon naught is common, so I'll keep it outside, 1 over 4 pi epsilon naught. So we have here Q1 over R1 plus Q2 over R2 plus up to Qn over Rn. Now we can write this term in the form of summation. So we have 1 over 4 pi epsilon naught, and we have here the summation I started from 1 up to n, and we can write it is Qi over Ri. This is the potential due to endpoint charges, where Qi is the value of the ith charge, and Ri is the distance of this ith charge from the point of question, from this point O. Now this is for the discrete form of charges, like we can count the number of charges here. But if suppose that this distribution, this charge distribution is not discrete but it's continuous, like we can't count the number of charges, then in that case we can replace this summation by integration. So I can write it as like this: if the charge distribution is continuous, if the charge distribution is continuous. We can't count the number of charges because the charges are infinite numbers. Then the summation in then the summation will be replaced by an integral. So we can, like, for discrete point charges, we have the potential V of R, which is equal to 1 over 4 pi epsilon naught sum over I started from 1 up to n, and we have Qi over Ri. This is for discrete charge distribution. Now if we have continuous charge distribution, then we can write it as V of R, the potential which is a function of position, which is equal to 1 over 4 pi epsilon naught integral of dq over Ri. Now this is for the continuous charge distribution. This is for continuous charge distribution. Now the continuous charge distribution can either be on the surface of a volume, or it can be on the surface of a plane, like on this surface, or it can be somewhere on a straight line. So for volume charge distribution, like if the charges are continuous but they are distributed on the surface of a volume, then we can replace this charge by its charge density, and the charge density will be volume charge density, which is equal to charge per unit volume dq over d tau, where d tau is for the volume. From this we can write dq is equal to rho d tau. So the above equation, I call it, let's suppose this is equation 1, this is 2, then 2 implies V is equal to 1 over 4 pi epsilon naught integral of rho d tau over R. Now for surface charge distribution, if the charges are distributed on this surface, let's suppose on the surface of this page, for surface charge distribution, now I'm sorry, I guessed this point wrong. For volume charge distribution means if the surfaces are placed in a surface which inside a volume, like inside the football or inside a tennis ball, then we have volume charge density, which is represented by this rho, which is equal to dk over d tau, where d tau represent the volume element. So this is for the volume charge distribution. Volume charge distribution. Now if the charges are distributed on a surface, like on this surface, on the surface of a football, or on the surface of a tennis ball, then we can replace this dq in equation 1 by sigma dA, where sigma represent surface charge density. So equation 2 become the potential, which is equal to 1 over 4 pi epsilon naught integral of sigma dA over R. And similarly for linear charge distribution, we replace this dq by lambda dl, where lambda represent linear charge density. So equation 2 become V is equal to 1 over 4 pi epsilon naught integral of lambda dl over R. This is for surface charge distribution, this equation. Charge distribution. And this is for linear charge distribution. This is all about potential due to endpoint charges or potential due to continuous distribution of charges. So I will stop my video here. Thank you.